So hi everyone, today I'm going to talk about SLX, an extended SLO framework to expedite incident recovery. So before we get started, let me do a short introduction about ourselves. My name is Qian, and together with me here today is my colleague Xuan. We both come from Ant Group as infrastructure SREs. So our job duty includes managing 60 plus more Kubernetes clusters, as well as other infra services like DNS, gateway, and PubSub. So to achieve our 5.9 availability target, we have to do lots of firefightings to solve all kinds of incidents. I think you would agree with this statement that any incident recovery is hard. And this motivates our talk today. So why incident recovery is difficult? We believe there are several reasons. The first, that we know the definition of incident is sometimes often ambiguous. Well, a typical situation is when your client or your upstream service started reporting errors or incident to your team that saying your service is broken, say may returning 500s unexpectedly, but you haven't received any alert or incident signals from your side. And this type of misalignment may delay the system recovery. And this is the first motivation. And secondly, let's say suppose both you and your client teams are investigating the incident. You assume this is a simple RPC failures due to a new rollout of your service. But when you try to roll back your service, you find out that you cannot do that because it actually depends on your client team's service to initiate. So right now their service is already broken and failing globally, and this entered into a circular dependency problem, which sounds really ridiculous, right? But this type of things happen every day, and because modern system architectures is already too complex. And this will definitely slow down your incident recovery. And sometimes, well, SREs may feel lost during the investigation among all those observation metrics and logs and dashboards, especially for those junior team members when they look at the dashboards that are not created by themselves. It may take a long time for them to figure out what the graph is actually telling them. So let's go back to the lifecycle graph. We all want to make the firefighting easier and more SRE friendly. We know we cannot prevent the incident from happening forever. Well, the black swan is always there, right? But we could build like say massive of observation tools or stacks to help us monitor the system, like the famous Prometheus, the Grafana, the OpenTelemetry, right? And we all have those. We have all those kind of say automation tools like Puppet, Ansible, Terraform, for us to like say automate or semi-automate the recovery process once you located the say the root cause or the broken rollout, right? But actually, the investigation stage is a real stage for SREs to demonstrate their capabilities. We know we cannot ask for a junior team member to tell the root cause at their first on-call rotation, right? It is just simply not fair. So our goal today is to build something that every SRE can benefit from it. So at least it can help shorten the investigation time. So what are our enemies or what are our challenges? Some of you may be surprised, but yes, our first challenge is to deal with numerous amounts of observation data, like metrics, logs, and traces. Because finding the root cause requires a lot of effort to walk through all kinds of metrics, say something like RPC error ratio, the memory usage, the CPU stats, and etc. It is like finding the needles in a haystack. So in the past, SREs have been advocating SLO concept to help build more specific metrics to reflect the service issues or represent the service health needs. The Google SRE workbook already described the use cases of SLOs, like using it for alerting, for detection, as well as for reporting. But still, the discussion focuses on each individual team and service. But when you actually investigate in practice or in reality, most of the time, you have to cross the team or the service boundary to check your upstream or downstream services. If we use Kubernetes as an example to debug a massive amount of pod creation failures, you may go through lots of different systems, right? You may wonder, like, say, if the master components, like the API server or the scheduler, is returning 500s, or maybe the code validation webhook is doing something wrong, right? So all of these debugging skills require a huge amount of cognitive load on your human mind. So naturally, you would think of using SLO data to reduce the cognitive load, right? At least, say, reducing the amount of metrics or data that SREs have to check. If the system boundaries, like say, are clearly defined, then if we put an SLO on each boundary and check them during incident, this may help us, say, quickly locate the pitfalls, right? However, dealing with one service is different than dealing with 100 ones, right? We also face the scalability issues of setting up SLOs. For example, our team manages 50 plus more components, and if each of them, say, have 5 key interfaces that we care about, and then if we have 3 types of basic SLOs, for example, the error rate, the latency, and the correctness, right? And have different requirements or different running environment, like canary environment, test environment, and prod environment. So together, in combination, how many SLOs do we need to deal with? Hence, we need to extend the SLO concepts into SLX. The key of this framework contains 2 parts. The first part is how to do a light-weighted SLO management for all services, and the other part is how to automate the metrics debugging based on anomaly detection and correlation. Why we call it SLX instead of SLO? So we introduced 2 new concepts in the SLX framework. The first one, we call it the service level factor. As you can see, the factor is constructed with an SLI metric and some specific conditions. An SLF contributes to the SLO computation arithmetically. The idea behind it is that once an SLO is broken, we can perform a factorization to figure out which factor contributes the most. So the other concept, we call it the service-level-dependency, which means the set of possible metrics that may break an SLO indirectly. For example, if the CPU of this HTTP server is burning, it may cause the error ratio or the latency to go up. Or if the downstream or the outgoing RPC for the HTTP API is serving more errors, it may cause the API itself to misbehave. So in a nutshell, anything that can cause an SLO to fluctuate, and the signal you cannot put it in the SLO formula directly, we treat it as a dependency for the SLO. Typically, it can be like downstream SLO, right? Well, I think a graph is better than 1,000 words. So we visualize the concepts of SLX. It is basically a dependency graph. The definition of SLF and SLDs are actually straightforward when you look at the graph. One thing to note is that most of the time, we can treat a downstream SLO as an SLD of the upstream SL. So this connects everything. Now the key to automate or semi-automate the investigation stage is to traverse the graph. So allow me to do a demonstration here. For example, if we see an SLO alert coming in this yellow rectangle, we know there is something wrong with this SLO, right? The first thing to do is to analyze which factor contributes to the alert. Note that simply sorting the contributed factors and pick the top ones may not help, since sometimes the SLO is already like having a very high level background error rate. You have to find out the spike or the abnormal one, which is the last straw that can break the camel's back. And this is when we need to use anomaly detection algorithms or the machine learning skills. Once we located the factor, we find out that there is another SLO that is also affected by this SLF. And this SLO is also an SLD of the original burning one. We can now narrow down the factor and feed the dependent SLO with the SLF to see if the dependent SLO is having trouble. If so, we can drill down more. And finally, we can go further. For SLOs that are connected, we can follow the chain and use anomaly detection to find out more time-correlated abnormal signals. And finally, we perform aggregation to list out all the possible causes and clues. And it can save SREs huge amount of time to jump over different metrics and tables and panels, right? So this is just a simple demonstration on the graph traversal. And next, I will hand over to my colleague Xuan to discuss more about our design and implementation of SLX framework.
Okay, so far we have learned the SLX graph and what it's capable of. Now we will try to define an SLX graph. Our goal is to automate everything, but we have to know how to do it by hand first. As we can see, the whole SLX graph is a faster cluck of entangled definitions. We have learned the definition of everything in this graph, but we have yet to find a neat way to describe such a graph, since everything is related to one another, and something will be changing constantly. For example, we might want to reset an SLO so that it is more practical, or we might want to substitute the SLI of an SLO for a better one, or we might want to add some SLD for an SLO. So how do we define this graph? The core component of this graph is actually not the SLOs, but the SLIs. All other definitions boil down to one single definition, that is the SLI. An SLO is just an SLI with a constraint. An SLA is a subset of the SLOs. And SLD is a relation between two SLOs. An SLF is actually a part of an SLI, a certain perspective of the SLI. So if we could perfectly define an SLI, we are able to define SLOs, SLFs, and even SLDs from that SLI. And more importantly, an SLI can be shared between different SLOs. You can define multiple SLOs on the SLI with different SLFs. For example, say we have an SLI for HTTP requests of some service. Then one can define an SLO for a specific cluster, or one can define an SLO for a specific client, provided that the SLI has those SLFs. So the main question now is, how do we define an SLI? An SLI is used to evaluate the status of the system at some given time. So it must be a function of time, which is a time series. And since it can have SLFs, it can be a multi-dimensional time series. So a metric can be an SLI, since a metric is a multi-dimensional time series, and we use metrics to evaluate the status of a system all the time. And with the SLI defined, SLO is just one step away. An SLO is an SLI with a constraint. First, we evaluate the SLI. Then we compared the evaluation with some threshold. So far, so good. But immediately things got complicated when we want to evaluate the status over a period of time. Take the success ratio for an example. We want to set up an SLO for the ratio of the successful responses against the total responses from the system, which is a very common use case. We cannot do that with a simple metric. Well, actually we can do that with one simple metric, but it is not easy to change the SLO with that one metric. Let's say we have a metric for the success ratio per minute. If we want to calculate the success ratio per hour, we cannot simply add them up to get an answer, since we lose information when we do calculations, like the ratio. So whenever we try to evaluate over a period of time on some ratio, we want to have the original time series to calculate that ratio. Then we have the definition of a complex SLI. It is two or more simple SLIs combined with an aggregator. This complex SLI is still an SLI, since it is still a multi-dimensional time series. And now we finally have our definition for an SLI and for an SLO. This is a sample of what we actually use for our SLI and SLO definitions. We first define the SLI, which is a complex SLI that comprised of two simple SLIs. This particular SLI is a success ratio SLI, which is comprised of an SLI for the error statistics and another SLI for the total statistics. This complex SLI can be evaluated for arbitrary periods of time as we need. Then we can declare SLOs upon that SLI. In this example, we declared an SLO for the pod creation success ratio over 30 days, and we declared a trigger that will set off an alarm when the error budget is depleted over a window of an hour. The idea of error budget is a bit more complicated and will not be covered here. Now that we have the definitions, what do we do about it? Our first goal is to have a set of dashboards on SLOs, and we are going to utilize the Kubernetes to automate the whole configuration process. The idea of the Kubernetes is that we can submit a declaration of some desired state to the cluster in the form of YAML configuration files, and there will be one or more controllers that will try to reconcile the current states of the cluster with the desired state. The Kubernetes also allows us to define our own reconciliation process using what is called the operator pattern. So what we can achieve with the Kubernetes is that we can automate the whole SLX definition process with a definition file and a controller. SLX is defined with a declaration file in YAML format, which is perfect for using Git as a version control tool. With the help of Git, we have the ability to see the version history, to review and comment on any changes, and to resolve any conflicts between multiple users. With Git and some widely used applications such as GitLab, we actually have a fairly solid interface for users to interact with. The Gitops is adopted fairly well in the Kubernetes community. With the help of the Argo CD, a community Gitops controller for the Kubernetes, we can easily achieve Gitops in our Kubernetes clusters. Argo CD will be responsible for synchronizing SLX declarations into the cluster, and the Kubernetes will reconcile the cluster with the declared SLX. Basically, it will configure a bunch of systems to accommodate the SLX declarations. The Gitops process we use is actually a bit more complicated. We introduced a unique two-stage Gitops process. First, we have a user-oriented Git repository. Then we have our Git repository for the SLX definitions we just discussed. The actual auto-synchronization between Git repository and the Kubernetes cluster happen on the latter Git repository. So why do we want the first repository, and how does it interact with our SLX repository? The main reason we want this repository is that although we can now define an SLX in YAML format, we have not simplified the definitions, so the users who use this repository directly have to be an expert. This is not what we want in the first place. We want to make our SLX accessible to everyone, so we introduced the first user-oriented Git repository that will house a much simplified version of the SLX definition for our entry-level users. And what connects to Git repository is the continuous delivery process that will render the simplified version into a full SLX definition, and in the meantime, submit a pull request to our SLX repository. What's more, we can actually have multiple user-oriented Git repositories for different groups of users. They can define their own CI/CD processes, and our SLX repository will have its own CI process to validate every pull request. Make sure all those SLX definitions submitted by the user repositories are correct. So let's sum up the workflow. First, our users, typically the SRE of some system and the stakeholders of that system, will set up some SLX by writing some YAML configuration files in their own user repository. Whoever commits a new change to the SLX, that change will be reviewed by the other party. And after the commit is merged, some magic will take place, and our users can enjoy their automatically generated SLX dashboards and most importantly, the alerts. So what happened behind the scenes? After the SLX definitions are merged into the SLX repository and synchronized to the Kubernetes cluster, our controller will take charge. The controller will generate Prometheus recording rules and alert rules as per the SLX definitions by editing some config maps in the cluster. And our Prometheus reloader will enable those rules within a minute. The controller will also create dashboards as per the SLX definitions through the RESTful API provided by the Grafana. After an alert is triggered, the event will be pushed to our AI system to analyze anomalies. The process of the anomaly analysis is something similar to what we have mentioned when we introduced the SLX Graph. This is an example of the dashboard generated. First, we have our overall success ratio graph and our error budget burndown graph. This section will be generated for every objective defined. We can have a 30-day burndown graph, or a 7-day burndown graph, or any period you want. Then we have sections for the underlying SLI. First, we have an overview on the SLI. We have the overall value, and if it is a complex SLI, we can see values from each component. Finally, we have a section for our SLFs. In this section, the SLFs of the SLI related to the SLO will be aggregated with different aspects, and from those aspects, we can find trace of the source of a failure. These graphs are very helpful. However, since we have introduced our AI system for anomaly analysis, these graphs are actually rendered useless in the production environment. Now they only serve as a guide for setting up a new SLO. So far, we have discussed what our SLX automation system can achieve. At the beginning, our SLX system can only provide some dashboards and alerts for the SREs. It is the SREs who respond to the alerts and analyze the data to identify and eliminate the failures. That is the L0 autopilot, which is no automation. Then we introduced an AI system for anomaly analysis. It can provide the SREs with probable root cause of the failure and even recommend solutions. This is the L1 autopilot. That is merely a driver assistance. The SREs still do all the ops after the failure. Our AI system is still in its infancy, and we have high hopes for it. The controller will be integrated with our AI system so that it should reconcile the cluster with the SLO, not just generate alert configurations and dashboards. That will be the L2 plus autopilot, that the system will heal itself without SRE interventions. Next, I will hand back to Qian to talk more about our practice on the anomaly detection.
Alright, thanks Xuan. Due to the time limit, I could not share too much details on the anomaly detection algorithms. We believe there are already many other talks and papers that present better than us. Instead, I will share a little about our understanding on the concepts. In short, I think this is just a simple formula. You try to get the three numbers right. The observation part is the data from your real monitoring systems, and the prediction part is computed from a statistical model or a machine learning prediction model, right? And then you perform a set of logical or numerical operations between these two parts and compare it with a predefined threshold. Sometimes the threshold is from a probability distribution, or sometimes it's just a simple empirical value. And that's it. Like what this graph demonstrates, the blue line is the real observation data points, and the green line is the computed predictive value. And the red line represents the threshold part. And then you compare them and you got two outliers. I'm not going to talk more about the algorithms, but I would like to share some common pitfalls we've seen in the past. The first thing is about data quality. We treat it as our top priority for anomaly detection if we want to use it correctly. A common failure is not handling the not a number scenario correctly. Sometimes in Prometheus, your query may result no data points in some time intervals, and you need to give it like a default value to avoid disconnecting the time series. And the second pitfall is that you have to watch out for the curse of dimensionality. When you try to analyze any time series, you need to check both the label keys and values. If they are not bounded, you may run into a computational problem when you try to do multi-dimension drill down or anomaly detection. Last but not least, please keep the anomaly detection algorithm simple and explainable. Sometimes you need to expose these parameters or these formula to your clients or whoever is using your framework, right? For example, why you should use 3 standard deviations instead of 4 standard deviations, right? We've seen cases when users want to tune their alerting or tune their anomaly sensitivity of their detection algorithm. And if you just throw more than 3 parameters to them, like say how many standard deviations, how to set up the alpha in the exponential moving average, or how to set up the time window, right? These parameters may drive them crazy and they may not happy with your algorithm or your product. So here are the key takeaways. First, SLO is not a silver bullet. It takes time to iterate to become a universal language in an organization or across multiple systems or services. Secondly, whenever you are facing a scalability problem like managing massive SLOs, automation and standardization are your friends. These are the foundation of all the other fancy stuff like machine learning and anomaly detections, and the algorithm part. And finally, do not forget to put your user first. Algorithms and machine learnings should not steal the spotlight of user experience. So with that, thank you all for listening.